Krankenhaus der Barmherzigen Brüder. Umsteigen zur Linie 5a.
Wir hören uns wieder. Jawohl.
Nein, ist noch nicht. Nicht die Haltestelle.
Ja, kein Glück.
Hotel Farbor, ist das eine oder zwei?
Ihnen sind schon aussteigen und noch vorgehen auf der Runde.
Ja, ja. Danke.
Dann meine auch noch Queen. Ja, dann habe ich die, also dann können wir am Pult an, oder nicht?
Das könnte sogar ich.
Schönes Wochenende.
Ich habe gerade für das Scheine. Sauber machen
Bin
sich
ich
gut ans
105
Steuer.
Jahre alt. Dann habe ich ein Recht auf Leben, oder?
Magistratisches Bezirksamt. Krankenhaus der Barmherzigen Brüder. Umsteigen zur Linie 5a.
So ist das aber, gell? Alles Gute, gell? Wir hören uns wieder. Jawohl.
Nein, ist noch nicht. Nicht die Haltestelle.
Ja, kein Glück.
Hotel Farbor, ist das eine oder zwei?
Ihnen sind schon aussteigen und noch vorgehen auf der Runde.
Ja, ja. Danke.
Dann meine auch noch Queen. Ja, dann habe ich die, also dann können wir am Pult an, oder nicht?
Das könnte sogar ich.
Schönes Wochenende.
Ich habe gerade für das Scheine. Sauber machen
Bin
sich
ich
gut ans
105
Steuer.
Jahre alt. Dann habe ich ein Recht auf Leben, oder?
Magistratisches Bezirksamt. Krankenhaus der Barmherzigen Brüder. Umsteigen zur Linie 5a.
So ist das aber, gell? Alles Gute, gell? Wir hören uns wieder. Jawohl.
Ja, perfekt.
Hotelfahrer, ist das eine oder zwei?
Ihnen sind schon steigen und noch vorgehen. Aber
Ja, ja. Danke.
Wenn ich meine auch noch will, ja, habe ich die, also dann können wir am Fuß an, aber nicht
Das könnte sogar ich.
schönes Hochbild.
Ich habe gerade für das eine.
Pass auf, was wir brauchen, wenn ich mittel
Frauen machen
bin
sich
ich
gut an
105
Steuern.
Jahre alt. Dann habe ich ein Recht, oder?
Magistratisches Bezirksamt, Krankenhaus der Barmherzigen Brüder. Umsteigen zur Linie 5a.
So ist das aber, gell? Alles Gute, gell? Wir hören uns wieder. Servus.
Nein, nein, ist noch nicht. Nicht die halbe Stunde.
Ja, perfekt.
Hotelfahrer, ist das eine oder zwei?
Ihnen sind schon steigen und noch vorgehen. Aber
Ja, ja. Danke.
Hello, and welcome back to the DAFx 2020, the first virtual DAFx ever. I'm Gianpaolo Evangelista, again, the chair of this conference, and today we will have a very brief program, only a matinee basically, with one session. Session 7. I hope you are all enjoying this conference, and we hope to have an in-person conference next year, but this year is we have to invent new ways of communicating our scientific ideas, development, and other social things, which will be much better next year, we hope. All right, so the program today is session 7 at 9:35, so in 4 minutes, on machine learning and analysis. We have had quite a lot of papers on machine learning, and not all the papers, as in the other sessions, will be presented. It was up to the authors to decide if they wanted to submit an audiovisual presentation of their paper. All the papers could be represented or presented for the first time next year in the hopefully in-person conference. Of course, there will be more posters due to time constraints that we will have, but nevertheless, I mean, there is a second chance to present papers. Then we will have, following each session, now it became like usual in this conference, we will have a coffee break with a question and answer session where the authors of the papers will have the chance to discuss in a live Zoom meeting with the session chair the questions that you in the audience have asked. You can ask, and you're welcome to do so. It's very interesting to ask questions in the live chat of the YouTube channel, which you will see on the right-hand side. There already people are saying good morning in that. Okay, so that is about it. And then at 11:25, or after the coffee break, after the question and answers, and possibly after real coffee, we will have the handover address, which is quite unusual this year, the form it will be. And then following, then basically a conference is over for the big audience. We will have a break and then a board meeting, which is not streamed anyway. So I hope you will enjoy the program today, and we can start with the announcement of the session. Session 7 is on machine learning and analysis, once again, and the session chair is Philip Esling. We will have 6 papers, and most of them centered on machine learning, except for on-set informed source separation. That is basically not a true machine learning paper, but only a music information retrieval kind of flavor. And then we will have also the TIV-lib, which is also more music information retrieval oriented, but so analysis basically. So I will now already announce the first paper.
Hello everyone, my name is Shahan Nersessian. I am a senior research engineer at Isotope, and today I will be discussing my work on neural parametric equalizer matching using differentiable biquads. First I will begin with some preliminaries, then I'll go over some parametric equalizer matching algorithms, and then we'll get into some experimental results and draw some conclusions based on these findings. So what EQ matching is when we try to transfer spectral qualities of a reference track to some source material by means of an EQ. And a very common approach for carrying out EQ matching involves an FFT. You have your source and your reference material, and you accumulate source spectra and reference spectra, and you can imagine dividing the time average source spectrum by that of the reference, and that will give you a desired magnitude response of the underlying equalizer. Now you can multiply incoming spectral blocks of the source by this magnitude response, and you've effectively achieved EQ matching. However, there are a few disadvantages to this approach. First of all, there's latency associated with FFT-based processing, as well as pre-ringing associated with zero-phase filtering. Arguably, the most common equalizer is the parametric equalizer. So a parametric EQ consists of a number of user-controlled bands, and the user generally would have control over band type. For each band, you can also adjust the frequency, the gain, and the quality factor for peaking filters or slopes for shelving filters. In this work, the band types that we will use for our equalizer will be fixed, in that we assume that we can have one low shelf filter, one high shelf filter, and some number of peaking filters. Now, the basic implementation of a parametric EQ can be carried out using a cascade of K biquads. And below, what we show is a 4-band parametric EQ consisting of 1 low shelf, 2 peaking filters, and 1 high shelf. So now we can delve into a little bit about the implementation of a parametric EQ using cascaded biquads. Biquads are second-order infinite impulse response filters. They carry out the difference equation that you see on the top left and have a system function, as you can see in the center. When we evaluate the system function by plugging in z equals e to the j capital omega, where capital omega refers to a vector of linear spaced frequencies from 0 to Nyquist, we can efficiently compute the frequency response of our biquad. We call this procedure freq-z, paying homage to its implementation in MATLAB and Python. There exists a procedure specified in the RBJ cookbook that we will call P2C that can convert frequency gain Q specification to the corresponding A and B coefficient vectors that you see in the difference equation. A parametric EQ, as we mentioned, can be implemented using K-cascaded biquads, and the composite system response will be the multiplication of the individual system functions. We can efficiently compute the composite magnitude response by means of the system function evaluation at z is equal to e to the j capital omega. Parametric EQ matching amounts to having a desired magnitude response x specified in dB and estimating a set of EQ parameters v hat such that the corresponding magnitude response x hat resembles x in some sense. For example, the mean squared error. V hat here is actually a concatenation of 3 vectors, v hat f, g, and q, which correspond to the frequencies, gains, and Qs for each of the bands in the parametric equalizer. It should be noted that the joint optimization of EQ parameters is a non-convex problem, and this is illustrated in the plots below. We generate a desired magnitude frequency response x by means of 2 peaking filters. And we can note that as we vary the parameters of the 2 filters and measure the deviation of their magnitude frequency response from the desired magnitude frequency response, that there exists a global minimum when the estimated parameters v hat match exactly the vector v that was used to generate this magnitude response. But there also exists a second minimum that is not the global minimum, and we can show what the error surface looks like as a function of frequency, and we can note that there are 2 valleys indicating the non-convexity of the problem. Now that we've discussed the parametric EQ matching problem, we're going to delve into a few different matching algorithms. We will begin with a baseline approach, which is a core DSP approach that uses a convex relaxation of the problem. So by convex relaxation, we mean that we can simplify the problem in some way such that we are ultimately solving a convex problem. And this is based on the work of Abel and Berners, who have made the observation that shelving and peaking filters are approximately self-similar on a log scale with respect to gain changes. And what it basically means is that the magnitude response of the equalizer can be expressed as a linear combination of what I'll call spectral bases. Given estimates of frequencies and Qs, we can generate this spectral basis matrix B, and we can solve for Vg in a least square sense. Of course, this approach will require a pre-estimation of frequencies and Qs, and in our implementation here for frequencies, we use a measure of spectral roll-off to determine shelving filter frequencies, and we look for spectral peaks to determine the frequencies for peaking filters. For Qs, we assume a constant slope for shelving filters of 0.75, and for peaking filters, we estimate Qs using suggested design equations by Abel and Berner. The disadvantage of this approach is that, first of all, it does not attempt to solve the non-convex problem directly, and the performance of the algorithm will depend on the accuracy of the pre-estimation procedure for frequencies and Qs. Now moving to our neural network approach, DAFx2019 really planted the seeds for this work. Last year, you might remember that Vesa Valimaki had presented a neural network to learn graphic EQ gains that was based on a parameter loss optimization. Then Philip Essling's group introduced their FlowSynth, and one of the main observations which motivated that work is that parameter losses are not directly correlated to perceptual quality. Then Jesse Engel had also given a keynote where he hinted work on differentiable digital signal processing, which will enable end-to-end training of audio machine learning models. And he even called out that IR filters were kind of an open area for further research. So what is this work doing? It uses DDSP concepts to formulate a parametric EQ matching model that can be optimized directly in the frequency domain. Here we see our neural network architecture. I will call out that the main novelty is highlighted in red. It is this differentiable cascaded biquad layer that allows the model to link estimated EQ parameters with their resulting magnitude frequency response. So the input to the network will be this desired magnitude frequency response, and it is passed through 3 fully connected stacks, which each consist of a dense layer, layer normalization, and a ReLU activation. And then the output of the last stack is subjected to a linear projection, and the output of this linear projection is split into 3 different vectors, which will ultimately correspond to our estimates of the frequency, gain, and Q vectors. The frequency, gain, and Q vectors are subjected to their own activations. We constrain frequencies to be within the audible range of hearing, so we use a sigmoid activation that is then scaled so that the output is always in the range of 20 Hz to 20 kHz. Gains are unconstrained during training, as we indicate by the identity operator. We allow ourselves the option to clip them to -10 to +10 dB during inference. Shelf slopes are constrained to the range 0.1 to 1 by means of a sigmoid activation and scaling, whereas peaking filter Qs are scaled to the range 0.1 to 3 in a similar manner. So when we concatenate these individual vectors, we get our estimated EQ parameters vector. But that's not enough, because we need to relate these parameters to their underlying magnitude frequency response. This is where the differentiable cascaded biquad layer kicks in. We implement the P2C and freq-z operations as differentiable operators using TensorFlow as our machine learning library of choice. And this allows us to create a parametric EQ frequency response evaluation layer that is fully differentiable. This means that the network can be optimized directly in the frequency domain, unlike other neural network-based attempts for performing EQ parameter inference. This gives rise to a pretty generalized objective function used to train the model, consisting of 3 terms. The first term is a frequency domain reconstruction loss comparing the desired magnitude response x and the estimated magnitude response x hat. The second term is a parameter loss comparing the true EQ parameters v and the estimated EQ parameters v hat. The third term is an optional L1 regularizer applied to the estimated gain vector, which promotes sparse solutions. Bands with sufficiently low gains could potentially be pruned during inference with minimal impact to the underlying magnitude response. Hyperparameters balance the relative importance of the different terms. And again, it is the novel, differentiable, cascaded biquad layer that allows for the first term to be optimized, meaning that it can be evaluated and its associated gradient backpropagated during model training. Now we will discuss the dataset used for training the neural parametric EQ matching model. We randomly sample EQ parameters and compute their resulting magnitude response. This allows for pairs of EQ parameters and their resulting magnitude responses as samples for training, and enables the use of both the frequency domain and parameter loss terms. We consider 2 distributions for sampling EQ parameters. An easier distribution, which generates desired magnitude responses that loosely resemble those seen in practice based on my personal experience. And these leverage a combination of beta and uniform distribution. There's a second distribution, which is more difficult to match to, where all EQ parameters are sampled using uniform distributions. And here the use of 2 distributions was intentional. We want to observe how well algorithms can work and generalize to distributions outside of the ones that they were trained on. Here we visually show the PDFs used for sampling EQ parameters. The training/validation set 1 has some intuitive distribution choices. For example, Low shelf frequencies are concentrated in the low end, and high shelf frequencies are concentrated in the mid to high end. You'll also note that the peaks in the gain distributions around 0 dB indicate that nodes are disabled with some probability. We ran experiments to validate the effectiveness of the proposed approach. We compare 3 different methods: the baseline approach, our proposed architecture using only a parameter loss, which is akin to some previous works, and our proposed architecture using a combination of losses, primarily weighting the frequency domain loss term L alpha. We generate new data points from both distributions to serve as 2 distinct validation sets. We see that the proposed network outperforms both the baseline and parameter approaches in terms of mean absolute and mean squared error in the frequency domain, effectively the perceptual domain of interest for our problem, on both validation sets. This is particularly interesting as the parameter loss of the parameter network is substantially lower than that of the proposed method, validating again the discrepancy between a parameter and end-to-end loss. Here we show select examples illustrating the effectiveness of the different approaches. Again, we see that the proposed method provides the closest matches, even though its parameter loss is much higher than the parameter network. While the parameter network can match the general shape of desired responses, it isn't precise enough and performs substantially worse than both the baseline and proposed methods. Lastly, we highlight one final real-world example where a guitar is recorded using 2 different microphones. In this case, the desired magnitude frequency response needs to be estimated, and our objective is to match one guitar tone to another. We performed this estimation of desired magnitude frequency response by dividing time average spectra after applying critical band smoothing to both the source and reference. Again, we see that the proposed method provides the best match, and in this case, the ground truth EQ parameters do not exist. In conclusion, we introduced a neural network approach for parametric EQ matching, where the novelty of our method is the implementation of differentiable biquads, which enable end-to-end training. The proposed method can outperform existing parametric EQ matching approaches, and it is because it attempts to solve the non-convex problem directly. Future work will involve classification of band types, whereas the band types in this work were fixed, the learning of the desired magnitude response directly from audio waveforms, and the use of differentiable biquads for other audio deep learning problems. Here are some select articles which we referenced over the course of this presentation, and thank you for your attention.
Hello, this is Blai Melendez, and I'm going to present the paper Relative Music Loudness Estimation using Temporal Convolutional Networks and a CNN Feature Extraction Frontend by myself and my supervisors Emilio Molina from BMAT and Emilia Gomez from the MTG. These are the sections of the presentation, and I will start giving some context with the introduction. Relative music loudness estimation is the task that consists in segmenting audio in blocks of 3 classes: foreground music, background music, and no music. This task is the necessary evolution of the music detection task, as in the copyright management business, the tax over broadcast music can be different for music played in the foreground and the background. BMAT offers a relative music loudness estimation service since 2016 and currently monitors more than 4,000 radio stations and TV channels 24/7. In this paper, we evaluate 2 different deep learning architectures for the task of relative music loudness estimation. The first one is a temporal convolutional network. This type of networks have the ability to model temporal context, which is a fundamental characteristic when working with highly temporally correlated signals such as music or speech. They also offer equal or better performance than recurrent neural networks and do not suffer from vanishing exploding gradient. The second network contains a temporal convolutional network, and it adds a front-end convolutional neural network that works as a feature extractor. Both architectures use the log-scale MEL spectrogram as input features. We compute the spectrogram from wave format mono audio at 8000 samples per second and a sample size of 16 bits. We use 128 MEL filters to convert it to a MEL spectrogram, and then we apply the logarithmic scale and min-max normalization so that each input ranges from 0 to 1. The final input has 128 frequency bins and 625 time frames, which is equivalent to 10 seconds. The temporal convolutional network is composed by 6 residual blocks. Each residual block includes 2 1D convolutional layers, has a higher dilation rate starting at 1 and increasing by a factor of 2 for each block, has n sub TCN non-causal 1D filters of length L, and has a dropout rate dr. The TCN architecture is ultimately composed by 1D convolutional layers, so it actually reads the log-scale MEL spectrogram as 128 temporal sequences of length 625, assigning every temporal sequence to a different channel. Its output is the probability of each class at each time frame. We assign to each time frame the class with the highest probability. A residual block applies a certain function f to an input x that depends on the weights w sub n and biases p sub n of the n layers contained in the residual block. The output of this function is then added back to the input x and passed to an activation function to obtain the output of the residual block y. This way, the layers inside the residual block learn modifications to the input instead of a complete transformation. This has proven to ease their optimization. We define the receptive field of a temporal convolutional network as the number of input timeframes that it considers to classify a single timeframe. It can also be defined as a temporal context used by the network to classify. The filters in the 1D convolutional layers are non-causal, so the receptive field is divided equally between past and future timeframes. As you can see in the example, each subsequent residual block has a higher dilation rate, starting at 1 and increasing by a factor of 2 for each block. So in this case, to classify a single time frame, the network considers 7 input time frames. The CNN frontend of the CNN-TCN architecture contains 7 convolutional blocks. Each convolutional block has one 2D convolutional layer with n sub CNN 3x3 filters, and also a max pooling layer that reduces dimensionality in the frequency axis by a factor of 2. The CNN frontend outputs n sub CNN feature maps with shape 1, 625. The temporal convolutional network then treats this output as n sub CNN temporal sequences of length 625 timeframes. Both of our proposed models classify at a frame level, and this makes them prone to produce noise in the form of short erroneous segments. That's why we apply a smoothing strategy to the output of our models, consisting in a sliding window that assigns the most represented class across all covered timeframes to its central timeframe. The experiment that we propose in the paper has the goal to find the best TCN and CNN-TCN models and to compare them to 2 baselines. However, we established 2 restrictions for our models. In order to know that any improvement comes from a more efficient usage of parameters through a better architecture, the number of parameters of the best TCN must be inferior to that of any baseline, and the number of parameters of the best CNN-TCN must be inferior to that of any TCN and any baseline. The experiment consists in 2 grid searches over several hyperparameters, and these 2 grid searches produce 40 TCN models and 80 CNN-TCN models. The dataset that we use to carry out this experiment is Open Broadcast Media Audio from TVs, also known as OpenVMAT. It includes 27 hours of broadcast audio distributed in 1,647 1-minute excerpts from TVs from France, Germany, Spain, and the United Kingdom. This dataset has been cross-annotated by 3 annotators and includes relative music loudness annotations. The content is distributed in 50% of foreground music, 35% of background music, and 50% of no music. It includes 10 predefined splits, from which we use 8 for training, one for validation and one for testing. We only use audio with partial agreement, which is the vast majority, and the ground truth is always the class with more agreement among the annotators. The baselines that we compare our models to are M1 and M2. M1 won the first place in the task of relative music loudness estimation in MIREX 2018 and the third place for the same task in MIREX 2019. M2 won the second place for this task in MIREX 2019. M1 and M2 have very similar architectures. They are both a convolutional neural network with 3 2D convolutional blocks, including a 2D convolutional layer and a max pooling layer, but they differ in the number and the shape of the filters of the 2D convolutional layers, which leads to a very different number of parameters. M1 has almost 98,000 parameters, and M2 has more than 453,000 parameters. The hyperparameters that we use for the grid searches are the number of filters of the 1D convolutional layers of the TCN, the number of filters of the 2D convolutional layers of the CNN, the length of the filters of the 1D convolutional layers of the TCN, and the dropout rate of the 1D and 2D convolutional layers. The training process for models and baselines is the same. We run the training for 100 epochs using the Adam optimizer with a learning rate of 0.001. We use a weighted categorical cross-entropy loss function to compensate for the imbalance of the training and the development sets. We shuffle training data after each epoch, and the batch size is equal to 128 instances. Most of the metrics that we use to evaluate our models come from the balanced version of the confusion matrix, which shows the percentage of content of each class classified as each class. From this confusion matrix, we extract the balanced accuracy as the mean of its trace and the precision and recall of each class. We also add an extra metric, the ratio of segments, that provides relevant information on how noisy a model is, regardless of how correct its predictions are. Its optimal value is 1, and it is computed by making the ratio between the total number of predicted segments over m files and the average number of ground truth segments for all annotators over the same n files. The first result of the experiment is the best model of each architecture. In the case of the TCN architecture, the best model has 32 1D convolutional filters of length 5 and a dropout rate of 0.15. The receptive field of this model is 4 seconds and the number of parameters is 85,635. In the case of the CNN-TCN architecture, the best model has 32 2D convolutional filters, 16 1D convolutional filters of length 7, and a dropout rate of 0.15. The receptive field of this model is 6.1 seconds, and the number of parameters is 80,963. The best TCN model after smoothing obtains 4.6 percentage points more in balanced accuracy with respect to M1 using 12.4% less parameters, and 3.2 percentage points more in balanced accuracy with respect to M2 using 81% less parameters. The ratio of segments shows that this model outputs 54% more segments with respect to the ground truth average. In the case of the best CNN-TCN model, also after smoothing, it obtains 8.4 percentage points more in balanced accuracy with respect to M1 using 17% less parameters, and 7 percentage points more in balanced accuracy with respect to M2 using 82% less parameters. The ratio of segments shows that this model outputs 14% more segments with respect to the ground truth average. In the left part of the graph, we can see that all CNN-TCN models obtain better balanced accuracy than all TCN models and the baselines. In the table below, there is an example that compares TCN best with the CNN-TCN that shares the same hyperparameters, and we can see that the CNN-TCN obtains better balanced accuracy using less parameters. In the right part of the graph, we can see that all CNN-TCN models obtain better ratio of segments than all TCN models. However, the baselines obtain the best ratio of segments because this graph is computed before smoothing. These high ratio of segments values happen because of the noisiness of frame level classification. In this last graph, we can see how the CNN frontend produces consistent patterns that identify different combinations of music and non-music content. See how the patterns are different when there is isolated speech, silence, mixed music and speech, or isolated music. In the bottom part of the graph, we can also see examples of the noisiness of the classification at a frame level. The conclusions that we can extract from this paper are that the usage of TCNs has led to a better performance with less parameters in comparison to the baselines. All CNN-TCN models outperform all TCN models even when using less parameters, which proves that the addition of a CNN frontend boosts the performance of the TCN. The addition of a CNN frontend helps producing a smoother classification in comparison to the TCN models, and that the CNN frontend produces consistent patterns that identify different combinations of music and non-music sounds. Thank you very much for listening to this presentation.
Hi, my name is Alec Wright, and I'm a PhD student here at Aalto University in Finland. And I'm here today to talk about a paper that we submitted to DAFx this year. It's titled Neural Modeling of Periodically Modulated Time-Varying Effects. As I said, we're at Aalto Acoustics Laboratory here in Finland, and I'm just going to jump right in. This presentation is about modeling time-varying effects using neural networks. First, I'm going to tell you about the model that we're using. Secondly, I'm going to talk about how we measured the LFO signal that we needed for this technique. And finally, I'm going to share some results with you. Time-varying effects that are modulated by a low-frequency oscillator, or LFO, are a popular choice for virtual analog modeling. These include phasors and flanges. The model that we're proposing is based on machine learning and can be applied to any target device as long as you can record training data from it. Firstly, I'm going to tell you about what I call the audio-only input method. So this is just one approach you might take, and I just want to tell you about it so I can explain the pitfalls and why the approach that we're suggesting is better. So you might start out with an input data set of clean guitar audio. You play that through the device that you're trying to model, such as this flanger pedal, and that creates your target data set, which is the audio that has been affected by the target device. And then you could just simply use this data set to train a neural network. However, this is going to be problematic. It's going to be quite hard for the network to learn in this situation because essentially there is another input to the effects unit which is controlling its behavior, the LFO signal. For network training, we generally want to process many batches of data in parallel. To do this, we might want to split up our data into short chunks of, say, 1 second in length. However, if we do this, the effects behavior will appear to be quite different in each chunk, as the phase of the LFO at the start of each chunk is going to be different. In addition to this, the trained model is not going to have any LFO control, so you won't be able to make the LFO go faster or slower, which is obviously not desirable. So our solution is quite simple, really. We can just annotate the input data set with the LFO. This way, when the audio is divided into short segments, the LFO, it's still at a different phase in each segment, but the neural network is being given this information, so it has all the information it needs to learn. So the resulting network is going to have 2 channels of input, the audio itself and the LFO signal. So this is a method that we're proposing in our paper, and one difficulty presented by this method is we need to estimate what the LFO signal is. That brings us to the next section of the paper, which is an accurate LFO measurement. So the LFO signal and phase need to be measured accurately. As you can see in this picture, if you imagine that the blue signal is the true LFO and the red signal is the predicted LFO, Any error in frequency is going to result in the LFO prediction error increasing over time. That's why it's quite important that we get an accurate method for estimating the LFO signal. Ideally, we'd like a measurement signal that is both short and also produces a high signal-to-noise ratio. In this paper, we use the impulse response of cascaded first-order all-pass filters. What this does is delays the different frequency components of the impulse over time, resulting in a kind of chirp. If you want to reconstruct the impulse from the chirp, you can simply reverse it and then put it through the all-pass filters. So if you just take these chirps and create a chirp train, you can then use this to measure the impulse response of the system as it changes in time. This is what it sounds like. So now I'm going to describe the measurement process. You take your chirp train and you put it into the device that you're trying to model. This produces an output that might sound something like this. Now, we can reverse this signal and process it through the all-pass filters, and this will give us a series of impulses, which now sound like this. Then you can just take a spectrogram of this signal, and you can see the LFO behavior quite clearly. This, however, isn't accurate enough for our purposes. Essentially, what we've done is sampled the impulse response over time. We can look at the notch positions, and they reveal the position of the LFO. If we follow a notch over time, essentially we're just sampling the LFO position. We use a chirp spacing of 30 milliseconds, which translates to a sample rate of 33.3 Hz. So we have the LFO position at each chirp time, and what we need to do is interpolate. This is because for our data set, we need to have the LFO position at each audio sample. We approach this by fitting a periodic function to the sampled LFO positions. The LFO is quite clearly a rectified sine wave, although it is upside down, it is a rectified sine wave. So if we just take this equation for the LFO and initially estimate the frequency using the fast Fourier transform of the measured LFO, then we use a nonlinear least squares algorithm from MATLAB to minimize the error. So to create our data set, we created a test signal, which is essentially chirp trains interspersed with guitar audio. And then what we can do is use these chirp trains to measure the LFO at the duration of the chirp train, like so, and then just extrapolate outwards. This gives us a fairly accurate prediction of what the LFO is doing in between the chirp train signals. So our final data set looks like this. We have the input data, which is 2 channels, the LFO signal and the input audio, and we have the target data, which is 1 channel. I'd like to point out that there are some discontinuities in the measured LFO signal that we achieved. So obviously this method isn't perfect. This is most probably due to noise introduced during the LFO measurement process. To validate our model, we created data sets for a phaser pedal and a flanger pedal. The recording process looks something like this. Identical output is sent out through output 1 and 2 and recorded through inputs 1 and 2. Input 1 records the target data set and input 2 records the input data set. Output 2 and input 2 are connected by a loopback connection. This is done to compensate for any latency that is introduced by the audio interface. Okay, now I can share some results of our method with you. For validation, we use a simple recurrent neural network model, which is very similar to one we proposed last year at DAFx. But I just want to point out that this method is not specific to this neural network model. It could similarly be applied to other neural networks. We trained neural networks with LSTM hidden sizes of 8, 16, 32, and 64. It took about 6 hours for training, and we use the error-to-signal ratio as a loss function. These are some of the results that we got. The real-time performance of our model is estimated based on results from a previous paper, which used a nearly identical model. In our previous work, we measured the speed of a C++ implementation on an Apple iMac. In this column, the time it took for this implementation to process 1 second of audio is reported. The error-to-signal ratio for each pedal is shown over here. In previous work, we found that, at least for amplifier emulation, an ESR of around 3% results in a model that is quite hard to distinguish from the target. In future work, we could do listening tests to further validate these results, but for now, I can just play you some sounds. Here we have some spectrograms taken from the phaser pedal, as well as from the smallest and largest neural network model. As you can see, at least for this case, it's quite hard to see a lot of difference in the spectrograms. Furthermore, I can play you some sound examples. This is some unprocessed audio. Here's the audio processed by the phaser pedal. Here's the audio processed by the smaller neural network. And here is the audio processed by the larger neural network. And I can just play you another example now as well. Here it is processed by the pedal. Here it is processed by the smaller neural network. And here it is processed by the larger neural network. So I think the model, whilst not perfect, does a pretty good job in this case. Here are some similar results for the flanger. So, in the spectrograms this time, it is possible to observe some differences. At these 2 points, for example, you can see quite a noticeable difference in the spectrogram. However, for the larger neural network, the difference is not there. But in this location here, you can see a difference between this and the larger neural network. And now I can play you some sound examples. Here it is with the flanger pedal. Here it is with the smaller neural network. And here it is with the larger neural network. And here's another sound example. And here it is with the pedal. Here it is with the smaller neural network. And here it is with the larger neural network. Next, we tried the neural network model with a time-varying LFO signal. So I'd like to point out here that the model so far has only been trained on an LFO signal of one frequency. So here's the input audio. And here is after being processed by the neural network with this time-varying LFO signal. So I think the behavior of the neural network is quite realistic at different LFO signal frequencies. Here's the same example for the phaser pedal. In this example, I can hear some undesirable volume fluctuation happening at the higher frequencies. I believe that if the neural network was trained with a higher frequency LFO, though, it would probably not produce this behavior. In summary, we found that time-varying audio effects that are modulated by a low-frequency oscillator can be effectively modeled by neural networks. The resulting models can run in real time. The main difficulty is measurement of the LFO, which is something which we could improve on in future work. If you want to hear more sound examples, there's a link written here, as well as in the paper itself. Thank you very much for your attention, and I hope to see you next year in person at DAFx.
My name is Yu Saka, Tokyo Institute of Technology. Today, I will introduce a new source separation method using new additional information. The main objective of this presentation is to develop an easy-to-use informed sound source separation method for extracting a specific instrumental sound from a monaural polyphonic sound. For monaural source separation, NMF-based methods have been studied well. NMF works well to extract vocal parts, but when extracting a specific instrumental sound from a polyphonic sound, it has difficulties in selecting the target instrument components. This is caused by the permutation problem and the non-correspondence between the instrument and the decomposed components. To solve this problem, informed source separation ISS has also been well studied. ISS utilizes various kinds of additional information to improve the performance, such as spectral patterns, musical scores, manual annotation, and humming. However, preparation of these type of information is time-consuming. Therefore, development of a user-friendly ISS method with easy-to-prepare information is necessary for practical applications. To achieve this, we introduce onset information as such additional information. The use of onset information has advantages compared to conventional informed source separation using music scores. First, it does not require any other information such as offsets and note durations. Second, onsets are easily inputted by tapping an off-the-shelf device. Of course, it will be tough to input all onsets manually, and the method should work properly with a partial set of onsets. As such a method, we propose onset-informed NMF or NMF. It is an extension of a standard NMF. The standard NMF decomposes the magnitude spectrogram X into two matrices, W and H. W is called a dictionary and corresponds to spectral components included in the spectrogram. H is called activation and indicates temporal changes of the corresponding dictionary components. ORNMF introduces onsets as binary masks. Binary masks are defined in a matrix form having the same dimensions as the activation matrix, and this onset matrix is element-wisely multiplied to the activation matrix. This means that the binary masks controls on and off of activation. In ORNMF, onsets are simply represented as the changes of the binary masks from 0 to 1 instead of the continuous changes of the activation. ORNMF is defined as a hierarchical Bayesian model. The output variables of ORNMF are dictionary W, activation H, and binary mask S, and these are estimated by a conditional posterior distribution P, W, H, and S given X in a Bayesian manner. Since this distribution is difficult to be calculated analytically, we adopted Gibbs sampling. Gibbs sampling draws samples of each variable artificially, then approximates the variable values by taking an average of the samples. Input onsets are converted into a binary matrix O, which has the same dimension as S. An element of O is set to 1 if an onset exists. The corresponding element of binary mask S, KT, is set to 1 when OKT equals 1. This slide explains the flow of the target source separation with ORNMF. The input is a polyphonic signal and a partial set of onsets of target instrument. The polyphonic signal is converted into a magnitude spectrogram by SDFT, and the onsets are converted into the onset matrix. After performing OINMF, these inputs are decomposed into two matrices, a dictionary matrix and an activation and binary mask matrix. The components corresponding to the target instruments are estimated as the ones starting from the timing of the onset as shown in here. By extracting the target spectrogram by multiplying these components and the corresponding activation, the target signal is reconstructed. Evaluation. To validate the proposed method, we conducted 3 experiments using MedleyDB. The first experiment confirmed the contribution of onset in target source separation. The second one investigates the robustness against missing onsets. The last one checks the robustness against onset deviation. As for metrics, we adopted an improvement in a scale invariant source-to-distortion ratio, SISDR. For each experiment, we selected 8 jazz pieces from the MedleyDB dataset. The titles of input jazz pieces are shown here. Each piece is truncated to a 20-second clip after downsampled to 22 kHz. Note that the percussive parts were removed by harmonic percussive separation in advance in this presentation. The onset timings of the target melody instrument were converted from F0 annotations provided by the MedleyDB dataset. I would like to start with showing a separation example. These figures are generated from the same 20-second clip. The first row shows the spectrogram of the input polyphonic signal. This polyphonic sound includes a clarinet, piano, bass, and drum sound. The second row shows the ground truth spectrogram for the target melody of the clarinet. The goal is to separate this target sound from the polyphonic signal. The third row shows the input onset matrix converted from the F0 annotation. The green bars indicate the onset timings of the clarinet. This is the estimated result. These red parts correspond to the element-wise product of the activation and the binary masks. The activation, you can find that the activation was estimated like a piano roll starting from the onsets. The last row shows the dictionary. In this case, 15 spectral components of the target instrument are obtained. This shows the reconstructed spectrogram of the target clarinet. We can find that the clarinet source was separated like the ground truth signal shown in second row. This slide shows the result of the first experiment. We compared the separation performance between 3 methods. 2 ORNMF methods with and without onsets and standard Bayesian NMF. The separation was performed 10 times per method and musical piece, and the average and the standard deviation were calculated. The blue lines are ORNMF with onsets, the red ones are ORNMF without onsets, and the orange ones are Bayesian NMF. ORNMF with onsets shows the positive values for all cases, while the other 2 methods show less than 0 dB. We can say that ORNMF outperforms other existing methods by using onset information effectively. The second experiment verifies the robustness of the proposed method for missing onsets. In practice, it is tough to ask a user to input all onsets manually, and the method should deal with a situation where only a partial set of onsets is available. we changed available onsets from 100% to 25% when applying OINMF. The results show that, in general, the mean of SISDR improvement tends to decrease slightly, and the standard deviation tends to increase as the missing onsets increase. However, the performance drops were maintained to be small. We confirmed that OINMF works properly even when only 25% of onsets are available. This slide shows the result of the last experiment. The related work reveals that human annotators have a tendency of 10 milliseconds delay and 0.1 second standard deviation in onset annotation. We simulated onset deviated by manual annotation according to this human tendency. The graph shows that the performance between deviated and non-deviated onset input is comparable except for bebop and modal jazz. On the other hand, one clip each for bebop and modal jazz failed to be separated due to the deviation. This result suggests that OINMF can deal with onset timing deviations which are expected in manual annotation. Summary: we propose an easy-to-use informed source separation method called OINMF to extract a target melody instrument. It utilizes only onset timing information as additional information, and it still works properly when a partial set of onset is available. We validated the effectiveness and robustness of OINMF through 3 experiments. In future work, we would like to compare the separation performance with the state-of-the-art methods such as deep learning-based separation. Also, we plan to conduct the subject experiments for practical use. Thank you for listening.
Hello and welcome to the presentation accompanying the paper Differentiable IR Filters for Machine Learning Applications. This paper was written by Julian D. Parker, Fabian Esqueda, and me, Boris Kuznetsov, at Native Instruments. We're going to start out by briefly talking about the paper that inspired this work, the DDSP paper done by Engel et al. At Magenta at Google. They introduced the concept of employing traditional DSP blocks within a machine learning context by implementing them in the differentiation framework TensorFlow. Given that most DSP blocks are composed of simple arithmetic operations, they can be implemented unmodified in a given differentiation framework and plugged into a neural network, enabling the use of backpropagation to set the respective coefficients. They implemented a harmonic oscillator, an envelope, and an FIR filter to construct a trainable filtered noise synthesizer. The key takeaway here is that by using specialized blocks like common DSP building blocks or from a general neural network building blocks such as an MLP, better results can be achieved for a given task while simultaneously using less resources. So in our paper, we took the main idea behind DDSP and applied it to IIRs, enabling the use of backpropagation to set the coefficients. We will also present a nonlinear case. Let's take a look at how we made IIR filters trainable. If we compare the difference equations of a simple RNN structure, the Elman network, and an all-pole linear IIR filter, we can see the obvious parallels. By removing the activation functions from the Elman network and setting the bias to 0, we get the all-pole IIR filter. This allows us to apply the techniques used to train RNNs unmodified to differentiable IIRs by simply implementing their difference equations in the differentiation framework, in our case PyTorch. What follows is a quick overview of the filter structures we chose to implement. First, we have a one-pole 1-0 first-order IIR. Its trainable parameters are B0, B1, and A1. Second, we have a transposed direct form 2 second-order IIR. Its trainable parameters are B0, B1, B2, A1, and A2. In this case, the filter topology is given, while the parameterization is free, as the coefficients are trained directly. Next is the state variable filter. Its trainable parameters are G, R, and the gains for the outputs. In this case, both the filter topology as well as the parameterization are given. For our last filter, we chose to implement an IIR in its state space form, which allows both the filter topology as well as its parameterization to be set by the learning algorithm. Its trainable parameters are the matrices A, B, C, and D. The order can be set by adjusting the sizes of set matrices. We call this form the LSS. Unlike nonlinear RNN networks, linear filters tend to go unstable very easily. To ensure this doesn't happen, we came up with several ways of randomly initializing the previously introduced structures. Random initialization has been shown to be very beneficial to training outcomes, which is why it's not enough to simply initialize them to one given known stable state. While these methods ensure that the filters are stable at the start of the training, it is possible for them to become unstable during. However, if we keep the learning rate sufficiently low, we can prevent this from happening. For more details on these initialization techniques, please refer to the paper. Alright, and now we take a look at the results. We trained each structure on a sine sweep mixed with white noise that was run through a series of different filters. For the nonlinear example, we ran a guitar signal through a Boss TS1 pedal and trained the network on that. For baseline, we employed a 1D convolutional network of varying sizes, which is essentially a trainable FIR. The plot at the top shows the reference frequency response as well as the responses of the baseline and the models we introduced. The middle plot shows the loss for each epoch the model was trained, and the bottom plot shows a linear 1D interpolation of the loss surface of the models. As we can see, the first order IIR has no problem fitting a first order low pass, though we can see that the IIR is struggling in the stop band for very high frequencies. This can possibly be remedied by training at a higher sample rate. The second order low pass case looks good for the SVF and the LSS, though not so much for the transposed direct form 2. If we observe the loss plot, we can see that the loss value for the direct form did not yet bottom out, so it is to be expected that it would also reach a similarly good result if trained for longer. However, this was not viable in the time we had. The parametric 3-band EQ case shows the biggest weakness of these structures when applied to a linear test case. While the SVF manages to fit the frequency response quite closely, it's still not a perfect match, while the LSS and the direct form filters struggle even more, especially for low frequencies. The loss plot also seems to suggest that a big improvement is not to be expected when training these for longer. Here, we want to emphasize that these structures are not meant to be used in a linear context or compete with traditional filter fitting techniques. The results we've seen so far are simply a proof of concept, showing that using backpropagation is a viable approach to set filter coefficients. The real use case of these structures is within larger, nonlinear neural networks. One use case of these trainable IIRs is nonlinear black box modeling. For example, when used in the Wiener-Hammerstein model. The Wiener-Hammerstein model is defined by nonlinearity surrounded by two linear filters. We can use a neural network to implement the nonlinearity. Any neural network can be used here, but as an example, we used an MLP with a depth of 2 and a width of 20, with the 10H activation function, and our differentiable IIR filters for both linear filter blocks. And indeed, when applied in such a nonlinear context, the filters perform quite well. As you can see, the waveform is matched quite closely by the structures using both the LSS and the SVF. And again, the direct form filter struggles the most. Let's have a listen to the outputs produced by the respective networks. So in conclusion, we introduced one first order, two second order, and one arbitrary order differentiable IAR, and showed that they can be successfully trained using backpropagation and used within a larger, nonlinear context. You can check out the source code for these structures at the following link. And finally, here are our key references. We hope that you enjoyed the presentation and thank you for your attention.
Hello everyone, my name is António Ramírez. I'm a PhD student at the Music Technology Group of Universitat Pompeu Fabra. Today I'll be presenting you the TIV-lib, an open source library for the tonal description of musical audio. This work is conducted by me, together with Gilberto Bernardes from Inesctec and University of Porto, Matthew Davis from CISUC from the University of Coimbra, and Xavier Serra also from the Music Technology Group of Universitat Pompeu Fabra. I'll start by describing tonality, which can be a system of relationships between a series of pitches forming melodies and harmonies, which have a tonic or central pitch class as its most important or stable element. Automatically characterizing the tonality of audio enables several applications like audio fingerprinting, music recommendation, retrieval of audio in large databases, harmonic mixing, chord recognition, structural segmentation, or even beat tracking. Normally, approaches for tonality description use chroma vectors as the representation. This divides the energy of the spectrum of an audio in the 12 tones of the Western chromatic scale, and at the end we get a 12-element vector where each element corresponds to the energy of each pitch class. On the right we see an image by Maynard Muller where we can see an example of a series of chromas in the bottom of the picture, which are synthesized from a C major scale. Several algorithms have been proposed to create this representation. One of these, the earliest one, is the pitch class profiles by Fujishima. A very common pitch class use is the harmonic pitch class profiles by Emilia Gomez. There's also the CRP and the NNLS chroma. And finally, the tonal interval vectors, which are not a chroma representation, but I will describe these on the next slide. The tonal interval vectors are inspired by geometrical models of tonal pitch, for example the ones proposed by Krumhansel, Lerdahl, Schuh, Hart, and they represent the n-node pitch configurations on a 12-dimensional space by a unique point, which is named the tonal interval vector. Besides having information about the pitch class, it also considers information about the intervallic nature of the audio. To calculate it, we take a chroma vector, we apply a discrete Fourier transform to it, and we apply some pre-calculated weights and the L1 norm, and finally we have the TIV. To unify the implementation of the tonal interval space and its features, we develop the TIV.lib. This allows to calculate the TIVs from any chroma representation. It's an open source implementation and both in pure data and Python, and can be accessed at my GitHub, which you can go through this link. We only have very common dependencies such as NumPy, and it's very easy to integrate the TIV-lib with common MIR libraries such as Essentia or Librosa, and you can see some examples of these inside the GitHub. From this tonal interval space, we can extract several features, and in this slide I present some of them. From the magnitude of the different components of the TIV, we can extract features related to the scale of a music piece, such as the diatonicity, chromaticity, or whole toneness. From this vector, we can also extract measures of dissonance, of harmonic change throughout a music piece, the key of an audio recording, and the Euclidean and the cosine distance between two tonalities of pieces of music. I will now detail a bit these features, starting with the TIV magnitudes, which, as I said before, represent the intervallic content of the TIV. It can be easily seen that a large magnitude in one of the coefficients of the tonal interval vector indicates how evenly the pitch profile can be divided by n over k, where n is the number of pitches in the pitch class profile and k is the component of the vector. Therefore, the first component corresponds to the chromaticity, the second to the diadicity, the third to the triadicity, the fourth has a meaning of a diminished quality, the fifth of diatonicity, and finally the sixth of whole toneness. One of the characteristics of the TIV mag is that it is invariant to transposition or inversion, and therefore all major triads or harmonic minor scales share the same Fourier magnitude and therefore the same TIV. As the magnitudes are invariant to transposition, we can use the phases to indicate the transposition which is under analysis. The function TIV combine, instead of forcing you to combine two audios and then calculate their TIV, it allows to do this process directly on the tonal interval vectors. There are then two distance metrics, the cosine distance, which is an indicator of how well two audios fit or mix together, and the TIV Euclidean distance, which is a very similar metric to the tone edge distance. Finally, we have the harmonic change, which outputs the harmonic change detection function, where we can see how much a track changes harmonically through time. To show the usefulness of the TIV lib in a clear use case, I'm gonna present you now an example of it. I will now play a short example of how the features that are calculated from the TIV relate to musical concepts. For this, I will play you Kraftwerk Space Lab, and this track starts in the whole tone scale and then moves to a diatonic one. In the background, you'll see the HPCP representation of the audio and three features: the chromaticity in white, the whole toneness in purple, and the diatonicity in orange. If you want to play around with the TIV lib and its features, we've created an example Jupyter notebook, which is hosted on Google Colab, and where we showcase several use cases for this library and how to run it and how to use it. It can be accessed at the link you see on your left. To sum up, I've presented you the TIV lib. We have a Python and a pure data implementation, and it can be used both in online and offline scenarios, and it's open source. So we are open to pull requests, and I will be really happy if you experiment with it a bit and give us your feedback. For future work, we want to investigate further on the pre-processing stages, which chroma representations work best for each situation, and we want to investigate its application on navigating large databases of sound, and we want to implement these on one of the most common MIR libraries, such as Librosa or Essentia. That's it for today. Thank you very much for your attention, and I'm looking forward to your questions.
So we thank all the participants on this session, all the presenters and authors. Thank you. And now, as is becoming tradition, we will have a coffee break where the question and answer session starts, dragging from the questions that you asked in the live chat. Just give us a couple of minutes to prepare this session over Zoom, and then we will come back to the stream. Thank you.
Okay, yeah. So yeah, I'll just kind of like quickly summarize. Purbhaditya had asked a question about parameter loss versus spectral loss. So which one is more important? The assertion here is that the spectral loss is more important, and you kind of have to have the end-to-end training to be able to enable that. Parameter loss does help a little bit in speeding up model convergence. And one interesting thing is that when I'm sampling EQ parameters, I have the parameters sorted by frequency, and that kind of breaks up any source of like permutations that can be confused by the network. And yeah, so it is enough to train with the spectral distance only, but if you can have the parameter loss in there, a small bit of it, it helps. And it's also the most natural thing to be sampling EQ parameters, so you will likely be having that in practice.
Okay, thank you very much. I think I'm gonna add a little question of my own there. Is just, I don't know if you've heard about the just noticeable difference loss, which is basically a perceptual loss that can be trained. Do you think you could include this type of more perceptually motivated loss, and how well it would work?
Yeah, I guess I'll have to know the exact details on the computation of it, but so long as it can be, you know, as long as you can write it in terms of differentiable operators, like the actual objective function can be whatever it is. Like if I kind of contrast this to Udo's and Purbhaditya's work, I think that actually they were optimizing impulse responses actually in the time domain. So like it's kind of one of these things that so long as you can set up the objective function in terms of differentiable operators, you should be able to do it.
Okay, thank you very much. Another question from Boris, which is, if I understand correctly, this approach requires an estimate of the desired magnitude response. Can you think of a way to employ your technique within a non-linear context?
Yeah, so this is kind of like getting to what I was alluding to in future works of being able to infer the desired magnitude response directly from the audio waveform, like having the neural net learn that. You can imagine that, like one use case that is kind of interesting that would fool an EQ matching algorithm, like if you wanted to really do timbral matching, is say you have some sort of wave shape at one frequency, and then you have a different wave shape at a different frequency. If you just try to accumulate spectrum and divide them, you're going to get something clunky happening. But depending on how you set up the data set and the kind of like comparator network between source and target materials, you might be able to come up with desired magnitude responses that yield more of like a true timbral matching than what we have when you just do kind of time accumulated spectra.
Okay, thank you. And one last question for your paper is, maybe I missed, could you insert your biquads designs into the DDSP for training and transformations, replacing, for instance, the FIR that filters the noise?
Yeah, I guess Boris answered that question a few papers later, that, you know, that these filters are amenable to that.
Okay, cool. So thank you very much, Shahan. I don't know if someone has one last question, maybe raise your hand. No, so we're going to move on to the second paper. So I don't know if Blai is here, because I see the name. Blai? Yeah. Okay, so we're going to, okay. So we're going to move to Alec, which I think is here. So,
Hello, I'm here.
hello. Okay, so thank you very much, Alec, presenting the neural modeling of time-varying effects. And I think we have a lot of questions for your paper. So the first question is, do you think it would be possible to estimate the LFO from the guitar audio in the future?
Yeah, yeah, I think that should be possible in theory. The nice thing about using a test signal is, you kind of know what you're putting in, so it's a lot easier to like measure the output. And then, as we did in the paper, you can then extrapolate that onto your guitar audio. But that's also not perfect. So it might be nice if you could actually estimate it directly onto the guitar audio as well. Yeah.
Okay, thank you. Then two questions from Julian Parker. which is first, LSTMs should be able to produce autonomous behavior if needed. Did you try to model the LFO as part of the network rather than as conditioning?
So I did not try to model the LFO as part of the network. It was something I considered, and I do think it is a possibility because then you wouldn't have to do the LFO estimation. I don't know if that would make the requirements of the model if it would need to be like more complicated to work well, but it's not something that I tried, no.
Thank you very much. And another question from Julian, which is flangers generally have quite a bit of memory, even if they're using a small BBD. The LSTMs you're using have much less. Did you notice how this impacted the model behavior?
Yeah, so I think that the way that the LSTM is achieving the flanging effect is just very different to how it's being done in a real flanger pedal. So it's not just delaying the input audio. I think essentially it's taking a kind of brute force approach where it just puts a bunch of filters on it. So you could see it if you looked at the really high frequency part of the spectrum, which wasn't really there in the guitar audio. But if I looked at it for like a test signal, you could see that it wasn't adding some of the filters, say like above 15 kilohertz or 10 kilohertz. So yeah, you could see the effects of that, I would say.
Okay, thank you. Another question from Shahan, which is, in practice, the user would control the LFO rate. In this case, you need to take this parameter and synthesize the LFO signal. Does this work, or is there a mismatch relative to the true LFO?
So we did do this a bit in the paper, and we found it seemed to generalize okay, but I haven't done a direct comparison with. It's harder to do a kind of A/B comparison if you're going to vary the LFO on a pedal because you don't know the ground truth as well. So yeah, I'm not sure, but it did seem to work, at least in our paper.
Okay. One last question for your paper, which is, would the LFO estimation work for effects involving multiple LFOs?
So I feel like it should in theory. I guess the extra challenges would be in measuring, kind of measuring that LFO signal, but I don't see why you couldn't just use two, instead of having trying to fit it to a single frequency LFO, you could just include a second component and try and add that as well. I don't see why not.
Okay, thank you. So I don't know if there is one last question for Alec in here. No, I've seen also that Bly is saying that the sound doesn't work, but the answer can be put in the chat. So Bly, if you make your sound work before the end of the session, you can tell us and I will give you the room, or otherwise I think, yes, you can maybe answer directly in the chat if sound really doesn't work. Okay. So yeah, maybe if you write your answer, I can then say it out loud for the public. I can be the transmitter. So moving on, we have the fourth paper by Yuta. So I think I saw Yuta connected. So yes, so the paper is onset informed source separation using non-negative matrix factorization with binary mask. And the question is actually from me. So maybe I'm not sure I got it right, but it seems you're using onsets, like onsets dataset. And the overall framework looks very similar to the onsets and frames ID, where the onsets are actually learned. So I was wondering, how do you think your method could compare or interact with onsets and frame?
Thank you for the question. Separation approach using onsets and frames that is musical score is called score-informed NMF. First, proposed method does not require offsets. So the burden on the user is smaller than the score-informed NMF. Second, proposed method can deal with the partially missing onsets. With the method using onsets and frames, it is expected that the missing nodes cannot be separated at all.
Okay, thank you very much for your answer.
Thank you.
So I don't know if someone has another question for Yuta in here. Nope, doesn't seem so. Thank you very much, Yuta, for the answer. Moving on to the fifth paper of the session, which is differentiable IR filters for machine learning applications, presented by Boris, which is here. Hello, Boris. So also quite a lot of questions and congratulations on new papers. So
thanks for that.
Maybe I'll start with the congratulations by Udo. And nice to enjoy your presentation and notation throughout the papers. And basically, the first question is from Shahan. I mean, two questions from Shahan. So first, can you comment on training speed and GPU utilization? In my experience, you can't cascade too many of these together.
Yeah, we have the same experience. So just in general, when cascading RNNs, the graph that gets generated is super huge, and it quickly fills up your GPU memory. You can kind of work around that or kind of remedy that in some ways by, for example, in PyTorch, you can use like tracing and their JIT, like translation layer, to improve performance. Or you could even think of doing custom implementations directly in CUDA, but we didn't try that yet. And then still the basic problem remains, like even with just the vanilla RNNs, you run into those kind of issues. You can just attempt to optimize that as much as possible. For the parametric EQ case, I think we cascaded 3 EQs, and the utilization was still, well, we didn't top it out yet. So if you accept like really long training times, I think you can cascade quite a lot of these parametric EQs. But obviously, at some point, there's a ceiling of where that's practical.
Okay, thank you very much. I'm going to add something to the question, but it's just a little addendum to this idea. So if I get correctly your presentation, you're seeing the IIR as an RNN, I mean a recurrent structure, right?
Yep.
So do you think you could use something like, I don't know if you know quasi-RNN, which is basically trying to implement recurrent structure as convolutions. And so you can actually kind of parse your whole structure directly, which might address this idea of GPU usage.
Yeah, I mean, maybe. I actually haven't heard of those, but it sounds something interesting we might look into.
Okay, thank you very much. Second question from Shahan, which is, makes sense that you may not need to ensure stability post-initialization since you train on a fixed configuration. But did you actually try to impose stability, and did it actually hurt performance?
Yeah, well, I mean, actually, we do have to make sure, well, the stability issue is not a non-issue during training. So especially if you use the LSS or the transpose diaphragm 2, you can run into instability during the training if your learning rate is too high. We did try and remedy that in the transpose diaphragm 2 case because it was pretty easy to enforce stability there. But what happened was that basically the gradients went to 0 when we approached the unit circle. So our models would just stop working at some point. Well, stop converging at some point. So we decided to take that out and to just put the learning rate quite low and then carefully choose a good optimizer. So the choice of optimizer is actually quite important for the performance of the models. We didn't really include that in the paper because we didn't do like a careful investigation of that. But just from intuition, we found that the Yogi optimizer worked quite well for almost all of the structures. So yeah, for the SEF, it's not an issue at all. I mean, it just doesn't go unstable if you just cap the parameters sensibly. Yeah.
Okay, thank you very much. So another question, because actually we had like 2 more questions while you were speaking. So okay. I'm gonna start by you're generating question, which is a great sign, I think. So one question from Alec, which is, first, thanks for the great presentation. And did you look at the input-output relationship of the trained MLP you used in Weiner-Ammerstein model? What did it look like?
We actually didn't, but we assume it's just some saturating nonlinearity, like some memoryless nonlinearity. We don't really think that the network we chose is the best choice for this. We really just wanted to see if these filters work at all within a nonlinear context. So we just chose like some random parameters that seem to perform well. But we could, I could pull them up, like not right now, but we could generate them and then get them to you.
Okay, cool. So additional questions from, sorry. Yes, why do you think that the direct form structure struggles the most?
I think that it gives the network too much freedom to move the poles and zeros. That would be my guess. Also, it tends to go. I think the way that the relationship between the transfer function of the filter and its coefficients is not so simple. So that's like more like a linear. It doesn't really go. It doesn't really transfer the shapes linearly or like in an obvious way. So I think that might be the problem. Yeah. I mean, then you would also expect the LSS to not perform that well, but it does perform quite well. So I'm not quite sure why that is. I mean, we do need a more thorough investigation of that. But I think it's just a too complex problem for the network to like trivially solve, basically.
Okay, thank you very much.
Oh. No, it's not working. Yeah.
Okay. Bly?
Okay. Yeah.
Yeah, it seems so. Oh, okay. So thank you, Bly. Okay, so Bly was actually presenting the second paper, which is relative music loudness estimation using temporal convolution networks and a CNN feature extraction frontend. So the question was, can the TCN be modified to become causal for real-time applications?
Yeah. We used Keras, and to do that, you only need to set the padding variable of the 1D convolutional layers to causal. So it's pretty easy.
It's pretty, okay. Okay, sorry. So yes, thank you very much, Bly, for making your microphone works. I don't know if there is an additional question right now for Bly. Not at the time. Okay, I will have a very large question in the end for most of the presenters there, but I'm keeping it only if we have time, because we still have one last paper, which was paper number 6, TivLib, an open source library for the tonal description of musical audio, which was from presented by Antonio Ramirez. I see your name, but I don't know if your sound works. Antonio, we can't hear you.
Can you hear me now?
Oh, yes, completely.
Sorry, I guess the gain was too low.
Okay. So my question for your paper is actually, do you think there are some particular applications to which these descriptors could be applied? And also, do you think there is application for symbolic music generation?
I think Matthew can later talk about the applications for the symbolic music generation. I think there were some things done in this domain already. But yeah, I think one very obvious application of this is some kind of augmented music listening. So when you're listening to music, you can sort of see some of the ideas the composer had behind, so you can see the scales that are being used or the intervallic content of the piece. And yeah, I mean, one very obvious application, I guess, that for me is the most interesting is enabling things like harmonic compatibility working very well. And you can have, let's say you are a music maker and you are making a music track and you want another loop that should fit in your composition, and you don't want to go all over the loops because most of them, I guess, won't be harmonically compatible. But with TIV, it should be very easy to find the ones that are less dissonant, or so the most consonant ones with the music piece you are working on. So I guess that really allows for quicker browsing of these large sample collections.
Okay. Thank you very much.
Then for the symbolic domain, I think Matthew can say something about that.
Yes, I can say something very quickly. Can everyone hear me okay?
Yes.
Yeah.
Okay, good. Yeah, just to pick up on that, thank you very much for Antonio for passing over to me. We've done some work already in the, I would say, like the basic tonal interval space, using this to drive some chord generation, some automatic harmonization. So one of the nice properties of the space is it allows a kind of user-defined choice of what chords might match at a particular time. We haven't really used it yet for melody generation or sort of more complex harmonization. But what I think is new and interesting here is these complementary features that we can extract quite easily from this representation, which are not so obvious to get out of other kinds of time frequency representations. And as Antonio says, I think these could be interesting kind of high-level parameters which would be understandable for someone with good musical expertise and maybe not a deep understanding of digital signal processing, let's say. So I think it does have some interesting potential there as a means to kind of, we could almost look at it as a kind of latent space which has some very understandable music theoretic parameters, but we are yet to experiment with that. But hopefully, watch this space. Okay. Thanks very much.
Thank you very much. I see that there is yet another question for Boris, which popped up on YouTube. Very successful lad today. So Boris, one last question, and then I think I have the time to ask my kind of meta question for everyone. So Boris, would the model work for extensions such as linearization of nonlinear state space?
I mean, that's basically what the LSS is. So it is a linearized nonlinear state space model, basically. So the answer would be yes.
Oh, wow. Efficient. Thank you very much. So actually, I have questions for most of the presenters. Sorry for those that doesn't include, because it relates to, I see there is a lot of success this year in this session, particularly, of course, in the kind of DDSP-like approach, which is to try to apply backpropagation inside, traditional digital signal processing. And I've been wondering, because we've been working also on DDSP with my team, and one question I have, which is completely unsolvable, I guess, but I'd like to have the advice and maybe generate a conversation around what I would call the applicability and the decidability issue. What I'm trying to ask is that at one point when we start using real life sounds, that are the result of a complex chain of effects, you can actually get the same sound from a variety of shifted effects and different generators, which means you can get to the same sound with lots of different, kind of DSP chains. So I'm wondering if you have some thoughts on this attribution issue, which we're going to get to when we go outside the scope of sine sweeps or very specific sounds. And how would you address it? And do you think it's going to be an issue?
Yes. Yeah, it's definitely an interesting question. I mean, I guess like I understand what you're getting at, and I guess one way of trying to skin the cat is by building up the entire processing chains themselves in DDSP and making sure that your training set is kind of varying all those components. I guess I don't have I think I can comprehend the problem that you're saying, but I can't really articulate the solution other than the fact that you need to kind of have like the arsenal of all the tricks that you plan to see in the real world being embedded in the model.
Okay. I don't know if you have anybody else has other thoughts on this question. It's a weird one, I know.
I'm not so sure if I understand it correctly, but if what you're getting at is like we're trying to feed in real world sounds into our models and have them adapt them, then we tried to do that for our paper actually. Like in the nonlinear case, we just put in a guitar signal and had a pretty successful fit with that. I think the problem with that is that you need to make sure that your input signal, as Shahan already mentioned, kind of traverses the whole possible space of all inputs that you could have and all combinations of them, which obviously you can't really do, I don't think. But you can tailor, I think, your input signals to whatever application you have. So, for example, if you do like a guitar pattern, obviously the majority of your training signals should be guitar-based stuff and not necessarily sine sweeps or drum loops or whatever. Okay. But I think it's totally possible to do, yeah.
Okay, because actually a follow-up question, which is still an open question, is that if you think about the space of all possible effects, let's say, and some of the sounds, for instance, simple synths can be modeled by almost any synthesizer and with few effects, and then some are super specific. So do you think we would gain from first having a model which could identify which effects are being used before having a model that should fit it?
If I could go, I think this is a really interesting question, and this is actually something that in my opinion, we discussed this with Julian and Fabian the other day. That's like one of the main strengths of the DDSP approach. Is the fact that you can constrain your neural network to the specific problem that you're having. So in that way, you can basically have way less overhead. So instead of having like a huge MLP with a convolutional network attached with an RNN or whatever, you can already make some, you basically have like a gray box model where your blocks are trainable neural networks, or trainable DDSP blocks. And you can adapt them to each problem. I don't know about having a network that would decide those blocks. I think, at least at the point we're at now, it's better to make like an informed decision by someone who knows the field. So, for example, we have knowledge of like a Moog synthesizer, like the way it's built up. So we can replicate its structure using DDSP blocks, and then have machine learning do the rest and tune the parameters of those. I hope that answered it.
Yes.
Yeah. The other thing that I think about is like sometimes like you can actually have the same synthesizer blocks, but depending on the application, you might want those like different synthesizer blocks to carry the weight in different ways. And then it kind of becomes on you of just like, how do you condition things in the network so that it kind of reflects how you expect those synthesizer blocks to be used in practice. So by like, that's like another like knob that you have to twist of like exactly what is the process of ultimately generating the parameters for each of those synthesizer blocks. And those, you can imagine that you have different things for different scenarios. And then if you wanted to automate those ones, then it becomes like some sort of upfront network that kind of keys into which path to go down or something like that might kind of exist. But at least the first path of just kind of having in that line of the tailor specific versions for different applications of just knowing that, okay, in this case, this synth might be carrying on this load more than that might be a way of taking care of that.
Okay, thank you very much. So I think we are almost up for time. There is maybe 2 minutes left. So yeah.
Another question online, would it be possible to create a DDSP formulation that is very general but employs strong regularization such that the optimizer focuses on those components that can achieve the objective? By from Team Loderos. Well,
actually,
we can leave it as an open question to everybody, I guess.
Because I think I have an idea on one, but I don't know if I'm sharing the session, so maybe I'm going to let the presenters take their take on this, but
I think it's kind of an open question. Nobody has the answer, probably.
Yeah, I don't know, if no one wants to answer, I can actually provide some ideas on this question, because I think the question we just asked and talked about was really correlated to this idea, which would be, and it kind of chimes really well with this onsets and frames idea. And, you know, when you condition actually one model by another, which is informing on the way the second model should behave. And for me, the only way to approach this very generic, like having a very generic formulation, leads to this kind of attribution. I say attribution, which means that basically you don't really know what is the right configuration of effects and chains of generation plus effects that you should use. So maybe having a first model that is just there to try to identify, oh, this thing has flanger, or oh, this thing has chorus. And then it could kind of, you know, impact the way the generation would behave. And I guess, I don't know if the team which asked the question has tried to implement DDSP, and I think DDSP works super well because it's actually super constrained. And the thing is, it works extremely well for violin, because basically you're using a sinusoid plus noise generator, right? So basically you already know in advance what you're going to model. So I guess for me, the real next step in this type of very signal-informed models would be to still keep as to multiple types of sound.
I actually think, not to derail this conversation, just to add to this, I think by building up a more generalized DSP model, we kind of go back to the problem that we're trying to solve by introducing the DSP in the first place. So if you want very generalizable models, just use, in my opinion, you can just use classic tried and true machine learning methods that already exist. The big advantage of the DSP is one, that it is so constrained and that we can tailor it to our problems very well. And two, that usually the parameters we get from there are very humanly interpretable. So of course you can build up a very generalized DDSP structure and then prune it. But I just don't see the point in that. I think if your goal is to have a generalizable model, you can just use regular machine learning models that have already been shown to work fine for that application.
I guess I'll give an answer that's somewhat in the middle. I think that even the Magenta people, they have kind of a follow-on work on their DDSP paper where they kind of have a general DDSP module, and they can use that to then kind of condition a second one and kind of take the general DDSP model and then distill it into the next one. They used it like to be able to like learn a pitch detector, like through analysis by synthesis, where they had just kind of a generic sinusoidal model, and then they fed that stuff about the sinusoidal model into the harmonic oscillator. So between those two models, they need to make this connection that I need to learn F0 to make it happen. So there is some world where there can be some form of model distillation with like very inductive biases that you kind of impose into the network.
I think we now have to move on a little bit, but we thank everybody. Interesting discussion that we can continue even next year with more results or
more
in
beer.
private or beer. Okay, thank everybody for the question and answer session. Very long and interesting this time. And congratulations to the authors of the papers. And now we switch to the famous or infamous handover address, which is today very particular. But thank also Philippe for chairing this session. Okay. All right, so this is the first time we have to hand over to the same organization. So basically the handover is handover to ourselves, which is the first time ever happened in DAFx. And it's true that I was already chair in one, I already chaired one of the DAFx's 16 years ago, so ages ago. But now I have to chair the hopefully in-person DAFx 2021. But in a retrospective, we'll give some statistics of this DAFx. So we received 69 submissions, basically in line with the previous DAFx, probably even Birmingham and Aveiro. 43 of them were accepted. We were pretty tough this time. I mean, we had a lot of reviewers. Each reviewer could review 1 or 2 papers, so there were there was also a second review chance, which is normally not done. In a way, we had a bit more time because we were not taken by the practical organization, but also we wanted to increase the quality. That has been discussed also in the board of DAFx, that the acceptance rate was a bit too high, and sometimes you had papers that were not really interesting. So we wanted to improve the quality. We felt that the system of sub-reviewers would create biased reviews, so that not truly independent, which is the system in which one reviewer calls other sub-reviewers. It did happen in some few cases by misunderstanding here in our reviews, but mostly they were all called by ourselves, and most of the time really true experts in the field, or sometimes just to test if the paper was readable by not very knowledgeable of the field people. So we have a 62%, which for me is like quite natural for a conference like this, and for a conference in which the scientific level should be really taken into high consideration. And so we want to thank the over 200 reviewers in the program committee, which are listed in the proceedings, if you're curious who reviewed, but not who reviewed which paper, but which were the reviewers in general, which were assigned only few papers, so they had more time to really focus on the one paper or two that they received. And we organized the second round of reviews, so that basically the authors had to really convince the reviewers that were critical that the paper actually was fixed in the right direction. Over 3/4 of the accepted papers were presented here, so there is 1/4 that was for different reasons of time or equipment or quality of the video or sound achievable from home equipment were cut out of this DAFx 2020. On the other hand, this gave us the possibility to avoid the poster presentation, which in an online session, an online DAFx, didn't really make sense, because you just have a very short poster and then people go in private chats to chat with the authors, which is not really interesting for me. There will be another call for papers for DAFx 2020 in 21. I have also to thank Stefania Serafin for deferring the foreseen DAFx 21 in Denmark. So we will stay in Vienna next year and hopefully have it in person, and we'll discuss in the board, I guess, the modalities in which this will work. But there is one thing that I made it clear: presenting in DAFx did not prevent from the same authors to present the same paper in 21, but hopefully the same authors will have new results, so they will say, okay, now we will present the paper in DAFx 2020 in 21. I think, anyway, this conference reached a large audience. We had, for the first day, and then every day, the increase, almost 1,000 views of the stream. And yesterday, for this other one, was for the second day, there were like 600, if I'm not wrong. So they will increase anyway, and so that the fact that the DAFx 2020 DAFx is free and open to everybody actually increased the audience, which is not a bad thing for our conference, to open up to the world, and maybe people who cannot, for logistical problems, to come normally to the DAFx, or for time reason, or for even money reasons, because it's becoming pretty costly to travel and go to conferences, so only groups with a certain amount of money can send people around. So I think it's quite a good idea, and it was reaching many people. So yeah, Stefania says DAFx in Copenhagen 2022. Of course, thank you. More on statistics, of course, the gender is still unbalanced, with slight improvement, like 5% of the authors are women in this DAFx, or in DAFx 20, because there are more papers that were not presented here. We are actively trying to counteract that by the inclusion grants, which will be travel grants and participation grants for the DAFx 20 in 21, for the live in-person conference, and to better distribute the tutorials, the keynote speakers, and session chairs among genders. Considering these special circumstances, sponsorship has been very generous. It was 2/3 than last year, and we hope to reach out to more companies for next year. Some companies say, oh, well, but we don't know how it's going this year. Let's talk about next year. when we will have the in-person DAFx. But anyway, we have to thank especially the companies that are listed here in every day beginning of the stream for really supporting us even in these special and difficult times for everybody. So big thank and clap. DAFx will not exist without their help, especially the in-person DAFx. This one was online, made at home, basically, and so almost at zero cost. So we wish to thank everybody who contribute to make this first virtual DAFx be a great success, the authors of excellent papers, the army of expert reviewers, the DAFx board, the sponsors, the local organizers, and you, the big audience. So thank you very much for this even very large participation in the live streams, and we hope, except for a few technical glitches about sound due to some, I mean, I am by myself here at home switching microphones on and off. You have thousands of buttons, and then be distracted by Zoom sessions in parallel with the streaming and the encoding of the stream. So it has been a bit complicated to operate without a sound engineer on my side, but I think it worked except for a couple of glitches, and I'm very pleased the actual internet streaming did not have any, except for 60 frames in 3 days were lost, were dropped, but they were buffered, so nobody realized that, and I think the whole thing worked pretty well. Is there a discussion? There is a question by Tim Loderos. Is there a discussion, forum, chat, or online community where DAFx authors can talk? I don't think so, except for the DAFx.de website. But we can talk about that. Tim, just email me. Email us at DAFx2020 some ideas, and we can actually actively create a forum on our website, most likely. So yeah, we will discuss this privately, but then I will announce it in public on the DAFx website. So please stay tuned even there. I mean, we also have a Facebook page, which many people adhered. We have many friends there, and you can become friend. Actually, that's a good starting point for the forum that you are asking for. So it's DAFx2020 is our DAFx 2020 page. So there we can start a discussion. And now Facebook has improved also in live. You can basically have video conferences and everything. So, okay. Thank you, Udo, for 3 times DAFx share. Well, so far 2 times. We will see. Okay. Well, anyway, so now in few minutes, in 5 minutes, we will have our board meeting, and thank you very much for your participation and contribution, and stay tuned. Really, this is a very nice community of people, very tolerant people. They are open to any difficulties or to any mistake or other things. So, okay. Thank you, and see you next year. But before that, maybe we'll see you on Facebook page with discussions and other things. We can periodically organize even some forum. Bye for now. To Vienna 2021. Thank you. thank you. I tried to interpret your clappings. Thank you, thank you. Nowadays it's the tradition in DAFx of the disappearing chair.